Hello there and welcome to Cosmos for Sleep. Tonight, we're gently exploring the profound origins of our universe, delving into 100 fascinating facts about the Big Bang. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy, and let's begin. The Big Bang, at its heart, was not an explosion in space, but rather the elegant and continuous expansion of space itself. It represents the moment when the fabric of the cosmos began to stretch and grow, carrying everything within it outward in a serene, unfolding dance. This distinction is subtle, yet profoundly significant. Imagine a vast, infinitely stretching piece of fabric that itself begins to gently expand in every direction. There is no single point where the stretching originates, nor is there an outer boundary it is expanding into. Instead, the very medium of existence, space-time, is gracefully increasing in scale. This grand, measured unfurling means that the universe has no discernible center or edge. Every point within its vast expanse experiences this expansion uniformly. From any vantage point, an observer would perceive all other distant galaxies gracefully moving away, giving the impression that they are at the center of this cosmic ballet. Yet every other point would feel precisely the same. It is a harmonious, symmetrical expansion, where every location is equally central and no boundary defines its ultimate extent. This cosmic journey of expansion has been ongoing for an immense duration. Our universe is approximately 13.8 billion years old, a span of time almost beyond human comprehension. Scientists arrive at this precise age through careful observations of the cosmic microwave background radiation, a faint echo from the universe's earliest moments, and by measuring the current rate at which space is expanding. These delicate measurements, taken together, allow astronomers to trace the universe's history back to its initial, incredibly compact state, providing a robust timeline for its grand evolution. To consider what existed before this profound beginning is to encounter a concept that stretches the very limits of our understanding. Before the Big Bang, the familiar concept of before as a measure of time simply did not exist. Time itself, much like space, came into being with the universe. It was not a pre-existing stage upon which events unfolded, but an intrinsic dimension woven into the very fabric of the cosmos as it began its expansion. Thus, when we speak of the universe's inception, we are speaking of the genesis of time itself, marking the inaugural tick of the cosmic clock. This suggests a serene, timeless void prior to the universe's awakening, a state where the very notions of duration and sequence held no meaning. In those primordial moments, the early universe was unimaginably hot and dense, a primordial sea of energy and fundamental particles. It was a state of profound intensity, a cosmic crucible where energy and matter were delicately interwoven, existing in an unfathomably compact form. Picture a tranquil, luminous plasma, so incredibly compressed that the fundamental forces of nature, which we now experience separately, were united, acting as one coherent entity. This was a realm where light could not travel freely, constantly interacting with the dense, energetic soup of nascent particles. It was a universe bursting with potential, a serene yet dynamic canvas waiting for the elegant brushstrokes of cosmic evolution to begin their work, transforming this unified energy into the diverse structures we observe today. The conditions were unlike anything we experience, a testament to the extreme beauty and simplicity of the universe's initial state. Curiously, the very name we use for this grand theory, the Big Bang, was not coined by a proponent, but by an individual who initially viewed the idea with skepticism. The term was originally coined by the renowned astronomer Fred Hoyle during a 1949 radio broadcast. He used the phrase somewhat derisively, intending to describe the theory's sudden, dramatic nature in contrast to his preferred steady-state model of the universe. However, despite its dismissive origin, the name was remarkably evocative and memorable, eventually becoming the universally accepted designation for the theory that describes our cosmic beginnings. It serves as a gentle reminder that even in scientific discourse, language can take on a life of its own, shaping our perception of profound concepts. It is important to remember that the Big Bang theory describes the universe's continuous evolution from a hot, dense state, rather than its absolute initial creation from nothingness. The theory provides a detailed and elegant framework for understanding how our universe has expanded, cooled, and developed over billions of years, transforming from a simple, uniform state into the complex tapestry of galaxies, stars, and planets we observe. It does not attempt to explain what sparked the initial conditions or what might have preceded them, but rather meticulously charts the unfolding journey of the cosmos from that initial state. It is a story of gradual change, of matter coalescing, of light emerging, and of structures patiently forming across immense stretches of space and time. This perspective offers a profound sense of continuity, portraying the universe as a dynamic, ever-evolving entity whose story is still being gently written with each passing moment. The Big Bang theory invites us to witness this majestic progression, from the earliest, most fundamental moments to the rich, diverse cosmos that cradles our existence. It is a testament to the universe's enduring capacity for transformation, a placid narrative of cosmic growth and graceful development that continues to captivate our minds with its elegant simplicity and profound implications. As the universe continued its serene expansion, a profound echo of its earliest moments remained, a silent, pervasive presence known as the cosmic microwave background, or CMB. This faint ancient light is not merely a memory, but a tangible glow that gently bathes every corner of the cosmos, stretching through the vast emptiness between galaxies and stars. It is an omnipresent hum, a gentle whisper from the dawn of time, carrying information about the universe when it was but a tender infant. This cosmic radiance truly permeates all of space, creating an invisible, comforting blanket that envelops everything within its reach. Indeed, the CMB represents the oldest light we can detect, a direct relic from the universe's infancy. This means that when we observe the cosmic microwave background, we are quite literally looking back in time to an epoch long before the formation of any stars, planets, or even galaxies. It is a venerable artifact, a cosmic fossil of photons that have journeyed across nearly 14 billion years to reach us, offering an unparalleled glimpse into the fundamental conditions of the very early universe. This ancient glow provides a profound connection to the initial state of the cosmos, a tranquil messenger from a time when the universe was a vastly different, far more uniform place. It is a silent testament to the enduring journey of light across unimaginable distances. The CMB fills the entire cosmos, arriving from every direction with a remarkable, serene uniformity. No matter where one might observe from within the universe, this gentle, pervasive glow would appear equally, symmetrically, and tranquilly present across the entire celestial sphere. This exquisite uniformity speaks volumes about the initial smoothness of the universe, a testament to the consistent conditions that prevailed in those primordial moments. It is as if the universe, in its infancy, was a perfectly still pond, with ripples only just beginning to form. This even distribution of ancient light is a cornerstone of modern cosmology, assuring scientists that the early universe was remarkably consistent in its properties, setting the stage for the structures we see today. Its accidental discovery in 1964 by two dedicated scientists, Arno Penzias and Robert Wilson, was a pivotal moment in astronomy, providing crucial evidence for the Big Bang. Working with a large horn antenna at Bell Labs, they were attempting to minimize all sources of noise for satellite communication experiments. Despite their meticulous efforts, a persistent, faint hiss remained, coming uniformly from every direction in the sky. Initially, they considered earthly sources, even speculating about pigeon droppings inside the antenna. However, after eliminating all conventional explanations, they realized they had stumbled upon something far more profound: the faint, cosmic afterglow predicted by the Big Bang theory. Their serendipitous discovery transformed cosmology, moving the Big Bang from a theoretical hypothesis to a well-supported scientific model, firmly anchoring our understanding of the universe's origins in observable evidence. It was a moment of quiet triumph, a confirmation whispered across billions of years. Furthermore, the CMB exhibits a nearly perfect blackbody spectrum, precisely matching theoretical predictions for a cooling universe. A blackbody is an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence, and then emits radiation based solely on its temperature. The fact that the CMB's radiation fits this specific spectrum with such extraordinary precision is a powerful confirmation of the Big Bang model. It indicates that the early universe was in a state of thermal equilibrium, behaving like a perfectly enclosed, hot oven that has been slowly, elegantly cooling and expanding over cosmic time. This spectral perfection is a beautiful validation of the physical processes that shaped the universe's earliest moments, a harmonious agreement between theory and observation. Today, after billions of years of cosmic expansion stretching and cooling this ancient light, its current temperature is a chilling 2.725 degrees above absolute zero. Absolute zero, the lowest possible temperature, is where all atomic motion theoretically ceases. The CMB's temperature, though incredibly cold, is a direct measure of how much the universe has expanded and cooled since its fiery birth. This pervasive coldness is a silent testament to the vast journey of cosmic time, as the initial intense heat has gradually dissipated across an ever-growing expanse. It is a universal thermostat, revealing the present thermal state of the cosmos, a gentle, almost imperceptible warmth that is spread across the entire observable universe. Yet, within this profound uniformity, there exist minute temperature fluctuations, variations of just a few millionths of a degree. These tiny ripples are not random noise, but are the delicate seeds from which all cosmic structures, like the grand galaxies and vast clusters we observe today, eventually grew. These subtle differences in temperature correspond to slight variations in density in the early universe, regions where matter was ever so slightly more or less concentrated. Over billions of years, the gentle, persistent pull of gravity patiently amplified these tiny primordial irregularities, causing matter to gradually clump together. This slow, elegant process led to the formation of the vast cosmic web, the intricate network of galaxies and dark matter that defines the universe's large-scale structure. These ancient fluctuations are, in essence, the universe's original blueprint, dictating how cosmic magnificence would unfold across the immense stretches of space and time. To understand how these subtle variations came to be, we must journey back to an even earlier, more profound epoch. Within an incredibly tiny fraction of a second after its inception, the universe underwent an extraordinary event called cosmic inflation. This was not a gradual expansion, but a momentary burst of incredibly rapid growth, a fleeting, powerful surge that reshaped the nascent cosmos. It occurred so swiftly that its duration is almost incomprehensible, lasting for perhaps a mere fraction of a second, yet its impact was monumental and foundational to the universe we observe today. This period of inflation is a cornerstone of modern cosmology, offering elegant solutions to several cosmic puzzles that were otherwise challenging to explain. It paints a picture of a universe that, in its very earliest infancy, experienced a dynamic and transformative growth spurt, setting the stage for everything that followed. During this brief, yet immensely powerful inflationary period, space expanded exponentially, stretching tiny quantum fluctuations to macroscopic scales, which then became the foundational blueprints for galaxies. Imagine the smallest, most ephemeral ripples in the quantum realm, almost imperceptible at their original size. Inflation acted like a cosmic magnifying glass, taking these minute, inherent uncertainties of existence and stretching them across truly vast distances. These now macroscopic variations in density and energy were not random, but were the very seeds of the universe's large-scale structure. It was a process of extraordinary elegance, where the most fundamental, subatomic uncertainties were transformed into the initial conditions for the majestic cosmic web of galaxies and clusters. This delicate imprinting during inflation ensured that the universe would not remain perfectly uniform forever, but would instead develop the rich, intricate patterns that define its structure. This rapid inflation also elegantly smoothed out any initial irregularities, explaining the universe's vast, large-scale uniformity. Before inflation, the universe might have been a chaotic jumble with vastly different temperatures and densities in various regions. However, the exponential stretching during inflation took these disparate patches and expanded them so dramatically that any local differences were effectively diluted and ironed out over immense distances. This process ensured that when we look out into the cosmos today, we observe a universe that is remarkably consistent in its properties, appearing much the same in every direction on the grandest scales. This profound uniformity, observed in the cosmic microwave background, is a direct and beautiful testament to the smoothing power of inflation, creating a harmonious and consistent cosmic canvas upon which galaxies could later form. Beyond smoothing out irregularities, inflation also resolved the flatness problem, suggesting that the universe's geometry is astonishingly close to perfectly flat. In cosmological terms, a flat universe means that parallel lines, if extended infinitely, would always remain parallel, much like lines on a perfectly flat sheet of paper. Without inflation, the universe's initial curvature would have had to be set with an almost impossible degree of precision for it to appear flat today. Inflation provides a natural explanation. Just as blowing up a balloon makes any small patch of its surface appear flatter, the immense stretching of space during inflation made the universe's overall geometry incredibly close to flat. This flatness implies a delicate balance between the universe's total energy density and its expansion rate, a balance that profoundly influences its ultimate fate, suggesting a future of continuous, gentle expansion rather than a dramatic collapse. Journeying even further back in cosmic time to the absolute infancy of the universe, we encounter the Planck epoch. This represents the very first moment of cosmic time, before 100,000 trillionths of a second. During this unimaginably brief interval, all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are believed to have been unified into a single, cohesive superforce. Our current understanding of physics, particularly quantum gravity, is incomplete for this epoch, making it a realm of intense theoretical exploration. It was a time of ultimate symmetry, where the universe existed in its most fundamental and undifferentiated state, a moment of profound unity before the graceful unfolding of its constituent forces. Following the Planck epoch, as the universe continued its incredibly rapid expansion and began to cool, gravity is believed to have separated from the other fundamental forces of nature. This event marks the beginning of the Grand Unification epoch. At this point, the remaining three forces, the strong, weak, and electromagnetic forces, were still unified as a single grand unified force, but gravity had begun its independent dance, acting as a distinct and separate influence. This separation was a critical step in the universe's journey towards the four distinct forces we recognize today, each playing its unique role in shaping the cosmos. It was a moment of elegant symmetry breaking, a subtle differentiation that would eventually lead to the complex interactions that govern all matter and energy. The electroweak epoch followed, witnessing the separation of the electromagnetic and weak nuclear forces. As the universe continued to cool and expand during this period, the unified electroweak force split into two distinct forces. The electromagnetic force responsible for light, electricity, and magnetism, and the weak nuclear force, which governs radioactive decay. This separation occurred at an incredibly high energy scale, a testament to the extreme conditions that still prevailed in the early universe. With this final decoupling, the four fundamental forces of nature, as we know them today, were fully established, each ready to play its part in the ongoing cosmic drama. This sequence of elegant separations, from a unified superforce to the distinct forces that shape our reality, is a beautiful illustration of the universe's gradual and intricate unfolding from its remarkably simple, yet profoundly energetic, inception. These early moments, though fleeting, laid the foundational rules for all subsequent cosmic evolution. As the universe continued its serene journey of expansion and cooling, new and fascinating developments began to unfold, bringing forth the very building blocks of everything we know. In the quark epoch, elementary particles such as quarks and leptons formed from the primordial energy of the universe. This was a time of immense energy, where the intense heat allowed pure energy to spontaneously transform into pairs of matter and antimatter particles, and then back again. Quarks are the fundamental constituents of protons and neutrons, while leptons include particles like electrons and neutrinos. This epoch was a dynamic, effervescent period, a cosmic dance of creation and annihilation, where the universe was a swirling soup of these most basic ingredients, constantly appearing and disappearing in a vibrant, energetic flux. The sheer density of energy in this phase ensured that these tiny, fundamental entities were born in vast numbers, laying the groundwork for the more complex structures that would emerge. A profound and curious aspect of this early phase is that the early universe is theorized to have contained nearly equal amounts of matter and antimatter. For every particle of matter, there was a corresponding antiparticle, identical in mass, but opposite in charge and other quantum properties. When a matter particle and an antimatter particle meet, they gently annihilate each other, converting their mass back into pure energy, typically in the form of photons or light. This delicate balance meant that if the universe had been perfectly symmetrical, all matter and antimatter would have completely cancelled each other out, leaving behind only a sea of light. The cosmos as we know it, with its galaxies, stars, and planets, would simply not exist. This theoretical prediction highlights a deep and fundamental puzzle at the heart of our cosmic origins. However, a crucial, subtle imbalance, known as the matter-antimatter asymmetry, allowed matter to slightly dominate and persist, forming everything we observe. For every billion pairs of matter and antimatter particles that annihilated, there was perhaps just one extra matter particle that survived. This minuscule excess, a seemingly insignificant deviation from perfect symmetry, was profoundly consequential. It was this tiny remnant of matter, left behind after the grand annihilation, that went on to form all the stars, galaxies, and indeed, all life in the universe. Scientists believe that this asymmetry arose from processes that subtly favored matter over antimatter during the universe's earliest moments, a mystery still being gently unraveled. This delicate cosmic preference allowed the universe to become a place of substance and structure, rather than an endless void of light. As the universe continued its gentle cooling, the conditions became suitable for the next significant step in particle formation. The Hadron epoch saw quarks combine to form more stable particles like protons and neutrons. Hadrons are composite particles made of quarks held together by the strong nuclear force. As the temperature of the universe dropped below a certain threshold, quarks could no longer exist freely, and instead bound together into these more familiar building blocks of atomic nuclei. Protons, made of 2 up quarks and 1 down quark, and neutrons, composed of 1 up quark and 2 down quarks, became the dominant forms of matter. This transition marked a shift from a fluid, energetic soup of individual quarks to a more structured environment of stable composite particles, setting the stage for the formation of the first atomic nuclei. Following this, the lepton epoch ensued, a period dominated by lighter particles such as electrons, muons, and tau particles. While protons and neutrons had already formed, the universe was still hot enough for these lighter leptons to interact frequently and exist in abundance. Electrons in particular would play a crucial role later in cosmic history, but for now they were part of a dense, energetic plasma. This epoch was characterized by a delicate balance between the creation and annihilation of these lighter particles, a cosmic dance that gradually shifted as the universe continued its unhurried expansion and cooling. The presence of these elementary particles in such vast quantities was a necessary precursor for the next major cosmic event, the forging of the universe's most fundamental elements. This leads us to one of the most remarkable and precisely understood events in the early universe: Big Bang nucleosynthesis, or BBN. This formation of the first light atomic nuclei occurred within the first few minutes after the Big Bang. As the universe cooled to temperatures around 1 billion degrees Celsius, protons and neutrons were able to fuse together through nuclear reactions. This brief, intense period of cosmic cooking lasted only about 3 to 20 minutes, but it was profoundly significant. During BBN, the universe patiently created the raw materials for all future cosmic structures. It was a time of delicate chemical creation, where the fundamental particles, born in earlier epochs, began to combine and form the very first, simplest elements. This process was a testament to the universe's elegant capacity for self-organization, transforming pure energy into the foundational matter that would eventually give rise to stars, galaxies, and all the complex chemistry of existence. The precise timing and conditions of BBN were critical, determining the initial cosmic abundances of these light elements, which, as we shall see, align beautifully with what we observe in the cosmos today. During this remarkable period of Big Bang nucleosynthesis, the universe acted as a grand, primordial forge, patiently creating almost all of the universe's hydrogen and helium, the two lightest and most abundant elements. Within those first fleeting minutes, as the cosmos cooled from its initial intense heat, protons and neutrons began to gently fuse. The vast majority of the protons remained as individual hydrogen nuclei, the simplest of all elements. Meanwhile, a significant portion of the remaining protons and neutrons combined to form helium nuclei, each comprising 2 protons and 2 neutrons. This process left the universe with a dominant composition, approximately 75% hydrogen and 25% helium by mass, a ratio that is still largely reflected in the cosmic landscape today. This elegant simplicity in the elemental makeup of the early universe provided the fundamental raw material from which all subsequent celestial wonders would eventually arise. Beyond these 2 primary elements, BBN also produced small, precise amounts of deuterium, a heavier isotope of hydrogen. Deuterium, sometimes referred to as heavy hydrogen, contains 1 proton and 1 neutron in its nucleus, unlike ordinary hydrogen, which has only a single proton. The formation of deuterium was a crucial intermediate step in the creation of helium during BBN. Its abundance is particularly sensitive to the overall density of ordinary matter in the early universe. By carefully measuring the amount of deuterium present in distant, pristine gas clouds that have not been significantly altered by stellar processes, astronomers can infer the conditions that prevailed during Big Bang nucleosynthesis. The delicate balance required to form just the right amount of this subtle isotope provides a powerful cosmic thermometer and densitometer, offering invaluable insights into the universe's infancy. Its precise quantity is a quiet testament to the finely tuned nature of our cosmos. Further elaborating on this cosmic alchemy, helium-3 and a tiny trace amount of lithium-7 were also gracefully forged during this brief, hot period. Helium-3 is another isotope of helium, containing 2 protons and 1 neutron. While less abundant than the more common helium-4, its presence provides additional observational constraints for cosmological models. Lithium-7, a much heavier and more complex nucleus, was produced in even smaller quantities. It represents the heaviest stable element that could be formed during Big Bang nucleosynthesis. The formation of these elements was a delicate dance of nuclear reactions, where temperatures and densities had to be just right for these specific nuclei to emerge. The precise observed ratios of all these light elements, hydrogen, deuterium, helium-3, helium-4, and lithium-7, serve as a profound fingerprint of the Big Bang, a unique chemical signature left behind from the universe's earliest moments. It is significant that the universe was simply too hot and expanded too rapidly for any heavier elements beyond lithium to form at this early stage. The conditions necessary for the creation of elements like carbon, oxygen, or iron require much higher temperatures and densities sustained over longer periods, typically found within the cores of massive stars. During Big Bang nucleosynthesis, the universe was cooling and expanding too quickly for these more intricate nuclear fusion processes to occur. The brief window of opportunity for fusion closed as the temperature dropped, effectively quenching the formation of heavier elements. This means that the primordial universe was chemically quite simple, a serene landscape dominated by hydrogen and helium, patiently awaiting the birth of the first stars to begin the grand process of cosmic enrichment. The absence of heavier elements in the early cosmos is as informative as the presence of the lighter ones, guiding our understanding of cosmic evolution. One of the most compelling pieces of evidence supporting the Big Bang theory is that the observed abundances of these light elements in the cosmos today align beautifully with the precise predictions of BBN. When astronomers study the oldest, most pristine gas clouds in the universe, or the atmospheres of ancient metal-poor stars, they find exactly the ratios that the Big Bang nucleosynthesis model predicts. This remarkable agreement is not a mere coincidence. It is a powerful and elegant confirmation of our understanding of the universe's earliest minutes. It demonstrates that the theoretical framework of the Big Bang accurately describes the fundamental cosmic chemistry that laid the groundwork for everything that followed. This alignment between prediction and observation is a testament to the scientific rigor and predictive power of the Big Bang theory, offering a profound sense of confidence in our cosmic narrative. Ultimately, these primordial elements were the fundamental building blocks, patiently awaiting the conditions for future stars and galaxies to form. The hydrogen and helium, along with the trace amounts of deuterium, helium-3, and lithium-7, constituted the raw, unrefined material of the early universe. For hundreds of millions of years following BBN, these elements would drift through the vast, dark expanse of the cosmos, slowly gathering under the gentle pull of gravity. They were the silent promise of future brilliance, the unformed essence of all celestial bodies yet to be. It would take the grand processes of stellar birth and death to transform this simple, primordial soup into the rich, chemically diverse universe we know, a universe capable of supporting planets, complex molecules, and eventually, life itself. These initial elements, born in a fleeting moment, held the quiet potential for all the cosmic wonders that would gracefully unfold over billions of years. As the universe continued its serene and unhurried expansion, it naturally began to cool, much like a gas gently expanding from a vast, primordial container. This steady decrease in temperature was a fundamental aspect of its early evolution, a patient transition from an intensely hot, energetic state to one where more stable structures could begin to form. Approximately 380,000 years after the Big Bang, this cosmic cooling had progressed sufficiently, reaching a critical temperature of around 3,000 degrees Kelvin. This temperature, while still incredibly high by earthly standards, was a profound threshold for the nascent cosmos, enabling a fundamental shift in its very nature. This cooling allowed free electrons and protons to gently combine, forming stable, neutral hydrogen atoms. Prior to this, the universe was a dense, electrically charged plasma, a swirling sea of unbound electrons and protons, constantly in motion due to the intense heat. However, as the temperature gracefully lowered, the kinetic energy of these particles diminished. The electromagnetic attraction between a positively charged proton and a negatively charged electron could finally overcome the disruptive thermal agitation that had kept them apart. With a subtle, patient embrace, these fundamental particles united, creating the first complete, electrically neutral atoms of hydrogen. This elegant process marked a transition from a chaotic, ionized state to a more composed, uncharged medium, a foundational step in the universe's journey toward greater order and complexity. This pivotal event is known as recombination, marking a profound shift in the universe's state. While the term recombination might gently suggest a rejoining of previously combined particles, it is somewhat a historical misnomer, as protons and electrons had not been bound together in this manner before. Nevertheless, this momentous transition was truly transformative. It signified the universe moving from a state where light and matter were inextricably linked and interacting constantly, to one where they could begin to exist more independently. Recombination was a cosmic turning point, altering the fundamental properties of the universe and setting the stage for all subsequent large-scale developments. It was a serene metamorphosis, shifting the cosmos from one essential form to another, with far-reaching consequences for its future. Indeed, before recombination, the universe was an opaque fog of charged particles, constantly scattering light and preventing its free travel. Imagine being immersed within an incredibly dense, luminous cloud, where visibility is utterly non-existent. In this primordial plasma, the free electrons acted as countless tiny, energetic obstacles. Photons, the particles of light, could not traverse more than a microscopic distance without colliding with one of these charged particles, being scattered, and having their journey interrupted. This continuous interaction meant that the universe was effectively impenetrable to light. It was a cosmic haze, a luminous veil that prevented any clear view through its vast expanse. Light was perpetually trapped, unable to embark on long journeys across space, making the early cosmos a uniformly glowing, yet utterly formless environment. However, after recombination, a dramatic and beautiful change occurred. Light could stream freely across space, rendering the universe transparent for the very first time. Once the electrons were bound within the newly formed neutral hydrogen atoms, they no longer presented the same ubiquitous obstacles to photons. Neutral atoms interact with light far less frequently and intensely than free electrons do. The universe suddenly cleared, much like a dense fog gently lifting to reveal a breathtaking and expansive landscape. Photons, once imprisoned, were now liberated to travel unimpeded, beginning their epic journeys across the cosmos. This newfound clarity was a monumental turning point, allowing light to carry information across vast cosmic distances, effectively opening a window to observe the universe's nascent state. It was a moment of profound liberation, transforming the cosmos into an open, perceivable realm. The cosmic microwave background, which we discussed earlier, is essentially a serene snapshot of this last scattering surface, the precise moment light was liberated. It is the image of the universe at the very instant it became transparent, a fossilized glow from a time when the universe was only 380,000 years old. Each photon in the CMB has traveled directly to us from that ancient surface, carrying with it the subtle imprints of the early universe's conditions. This last scattering surface represents the farthest back in time we can currently see directly with light, as anything prior to it was shrouded in the opaque cosmic fog. It is a venerable message, a silent photograph capturing the universe's initial clarity, offering a profound and direct window into its distant past, revealing its tranquil, uniform beauty. This newfound transparency was absolutely essential for the eventual formation of the first stars and the subsequent structures of galaxies. In the opaque early universe, the trapped light exerted a significant outward pressure that effectively counteracted the inward pull of gravity, preventing matter from clumping together efficiently. With light finally free to escape and travel across the vastness, this counteracting pressure diminished, The universe could then continue its cooling process more effectively, and gravity could begin its patient, subtle work of pulling together the slight overdensities of matter, which were the delicate seeds of future cosmic structures. Without this crucial clearing, the universe might have remained a uniform, featureless expanse, forever devoid of the luminous galaxies and stars that gracefully adorn our night sky. It was a necessary step, a moment of profound liberation that allowed the universe to begin its grand journey of self-organization and creation, paving the way for the complex and beautiful cosmic tapestry we inhabit today. This quiet unfolding of cosmic properties was a prerequisite for all the stellar births and galactic formations that would follow, a testament to the universe's elegant design. With light now free to travel, the universe entered a new, yet paradoxically serene phase. Following recombination, the universe entered a period known as the Cosmic Dark Ages, an era of profound darkness. This was a time when the universe, having cooled sufficiently for neutral atoms to form, no longer glowed with the uniform brilliance of the primordial plasma. The light from the Big Bang had already journeyed far, and the first stars and galaxies had not yet awakened to illuminate the vast cosmic expanse. It was a hushed, expansive period where the cosmos, though transparent, remained largely unlit, a silent canvas awaiting its first strokes of luminosity. This darkness was not one of emptiness, but rather of a subtle, pervasive quiet, a gentle pause before the grand cosmic symphony truly began. During these hundreds of millions of years, there were no stars or galaxies to emit light, only vast clouds of neutral hydrogen and helium gas. Imagine a universe filled with an ethereal, invisible fog, composed of the very lightest elements forged in the Big Bang. These enormous diffuse clouds drifted silently through the cosmos, gradually growing denser under the patient, subtle pull of gravity. There were no bright beacons, no swirling galaxies, no familiar celestial objects to break the monotony of the pervasive gloom. This was a truly quiescent period, a time of cosmic stillness where the raw materials for future brilliance were slowly, imperceptibly gathering. It was a universe in its slumber, a period of profound potential, where the seeds of future light were slowly germinating within the vast, dark cradles of gas. This dark period persisted for several 100 million years, a quiet prelude to the universe's illumination. From Takas, stretching to about 400 to 500 million years later, the cosmos remained largely in this state of gentle obscurity. It was a long, unhurried wait, a vast expanse of time during which the invisible forces of gravity steadily worked, patiently drawing together the neutral gas clouds. These clouds were not completely featureless. They contained the subtle density fluctuations imprinted during cosmic inflation, which served as gravitational magnets, slowly accumulating more and more matter. This patient assembly of primordial gas was a necessary stage, a gradual buildup of material that would eventually reach the critical mass and density required for the universe's first luminous awakenings. Then, after this prolonged period of gentle darkness, the cosmic dawn began when the very first stars gently ignited, gradually piercing and ending the long dark ages. This was a truly momentous epoch, a quiet but profound transformation that brought the first glimmers of light to a previously unlit cosmos. Deep within the densest knots of the accumulating gas clouds, gravity's persistent embrace finally triggered the collapse and compression of matter, raising temperatures and pressures to the point where nuclear fusion could begin. With their birth, these pioneering stars became the universe's first beacons, slowly pushing back the pervasive gloom and introducing luminosity into the vast, silent expanse. It was a serene and majestic awakening, a gradual unveiling of the universe's inherent brilliance, marking the end of its long, quiet slumber. These pioneering stars, often referred to as Population 3 stars, were incredibly massive and intensely luminous. Unlike the stars we observe today, which contain a mix of hydrogen, helium, and heavier elements, These first stars were formed almost entirely from the pure, primordial hydrogen and helium forged during Big Bang nucleosynthesis. Being so massive, they burned through their nuclear fuel at an extraordinary rate, radiating immense amounts of energy. Their short but brilliant lives were like fleeting cosmic fireworks, each one a powerful, solitary beacon in the otherwise dark universe. Their intense radiance was a stark contrast to the surrounding emptiness, making them extraordinary celestial pioneers, destined to live brief, dazzling lives before gracefully returning their enriched material to the cosmos. Indeed, they were composed almost entirely of the primordial hydrogen and helium forged in the Big Bang. This lack of heavier elements, often called metals by astronomers, meant that their formation and evolution followed a slightly different path than later generations of stars. They were simpler in their composition, purer reflections of the universe's initial chemical state. These stars were the universe's first alchemists, taking the basic ingredients of hydrogen and helium and, through the process of nuclear fusion in their cores, beginning to forge the very first heavier elements like carbon, oxygen, and iron. This was a crucial step in the chemical evolution of the cosmos, as these elements are essential for the formation of planets and, ultimately, life itself. Their existence marked the beginning of the universe's chemical enrichment, a subtle yet profound transformation of its fundamental makeup. The intense ultraviolet radiation emitted by these first stars began the process of reionizing the surrounding neutral hydrogen gas, just as the universe had become transparent after recombination. It was now being transformed again, but this time by the powerful light of its first luminous inhabitants. The energetic ultraviolet photons streaming from these massive, hot stars had enough energy to strip electrons away from the neutral hydrogen atoms in the surrounding clouds, turning the gas back into an ionized plasma. This process, known as reionization, gradually cleared away the remaining cosmic fog, making the universe truly transparent to all forms of light. It was a gentle, sweeping action, a cosmic cleansing that allowed light to travel freely across the vast distances, illuminating the emerging structures and paving the way for the grand galaxies to shine brightly across the cosmos. This reionization was a testament to the transformative power of starlight, a beautiful interplay between the birth of stars and the changing transparency of the universe. As the first brilliant stars began to illuminate the cosmos, they initiated a profound and sweeping change that would forever alter the cosmic landscape. Reionization was the process where powerful ultraviolet light from the earliest stars and galaxies stripped electrons from neutral hydrogen atoms. Imagine tiny, energetic packets of light, photons, streaming forth from these nascent stellar nurseries. These photons carried enough energy to gently knock electrons free from their atomic bonds within the vast clouds of neutral hydrogen gas that pervaded the universe. This delicate liberation of electrons transformed the gas from an electrically neutral state into an ionized one, a plasma where electrons and protons once again floated freely, though now in a much less dense and rapidly expanding environment. This ongoing process was not instantaneous, but a gradual, pervasive transformation that slowly swept across the entire cosmos, reshaping its fundamental character. This profound transformation shifted the universe from a neutral, opaque state back into an ionized, transparent plasma. Before reionization, the neutral hydrogen gas had absorbed much of the light traveling through it, rendering the universe largely opaque, like a dense, luminous fog. However, as the intense ultraviolet radiation from the first stars and galaxies permeated the cosmos, it created vast bubbles of ionized gas. Within these bubbles, light could travel freely, unimpeded by the scattering electrons. Over time, these bubbles grew and merged, eventually encompassing the entire universe. This reionization effectively lifted the cosmic veil, allowing light to journey across immense distances without constant obstruction. It was a beautiful return to a transparent state, but this time, the transparency was driven by the radiant energy of newly born stars and galaxies, rather than the simple cooling of the Big Bang's afterglow. This transition was crucial for the universe to become the observable, light-filled expanse we perceive today. This reionization process was gradual and extended, taking hundreds of millions of years to fully complete across the cosmos. It did not happen uniformly or all at once, but rather unfolded like a slow, deliberate sunrise across the vast cosmic canvas. Patches of the universe became reionized first, typically in regions where the earliest, most massive stars and galaxies had formed. These localized sources of powerful ultraviolet light created expanding ionization fronts that slowly carved out transparent regions in the surrounding neutral hydrogen. Over time, these pockets of clarity grew, merged, and eventually percolated throughout the entire universe. This extended timeline, stretching from approximately 400 million years to about 1 billion years after the Big Bang, highlights the immense scale and patient nature of cosmic evolution. It was a period of subtle, yet relentless change that fundamentally reshaped the universe's ability to transmit light and information. During this era, the earliest galaxies were likely smaller, more fragmented, and irregular than the grand, organized spirals we observe today. These nascent galactic structures were still in their infancy, having only recently coalesced from the primordial gas clouds under the gentle, persistent influence of gravity. They lacked the mature, well-defined spiral arms or elliptical shapes characteristic of older, more evolved galaxies. Instead, they were often clumpy, chaotic collections of gas, dust, and newly formed stars, perhaps resembling a series of brilliant, scattered jewels. These early galaxies were the universe's first attempts at large-scale organization, slowly learning to assemble and evolve through countless interactions and mergers. Their irregular forms are a beautiful testament to the universe's emergent complexity, showcasing the initial, raw stages of galactic development. These nascent galaxies were also vigorous sites of star formation, slowly enriching the cosmos with the first heavier elements. Within their fragmented structures, dense pockets of gas continued to collapse, giving birth to generations of new stars at a prolific rate. These stars, particularly the massive ones, lived short, brilliant lives before gracefully ending in supernova events. These cosmic explosions were vital. They acted as the universe's first chemical factories, scattering the newly forged heavier elements, such as carbon, oxygen, and iron, into the surrounding interstellar medium. Over time, successive generations of stars formed from this increasingly enriched material, leading to a gradual increase in the abundance of these heavier elements throughout the universe. This slow, patient process of cosmic recycling laid the chemical foundation for the eventual formation of rocky planets, and ultimately, the complex chemistry necessary for life itself. Today, the light from these first galaxies is now incredibly distant and stretched by cosmic expansion, appearing as faint, red-shifted infrared signals. Because these galaxies are billions of light-years away, their light has been traveling for an immense duration, spanning the vast majority of cosmic history. As this light journeys across the expanding universe, its wavelengths are elongated, or red-shifted, shifting it from the visible spectrum into the infrared. This cosmological redshift acts as a powerful cosmic odometer, indicating both the distance to these ancient galaxies and the age of the light we are observing. To detect these faint, stretched signals, astronomers rely on highly sensitive infrared telescopes, both on Earth and in space, such as the James Webb Space Telescope. By patiently gathering these elusive infrared whispers, scientists can peer back to the very beginnings of galactic formation, offering invaluable insights into the universe's early evolution and the serene awakening of its luminous structures. This distant, ethereal glow provides a profound connection to the universe's formative years, a gentle reminder of its long and majestic journey. As the universe continued its graceful expansion and the first stars began to shine, another fundamental process was quietly unfolding, shaping the cosmos into the intricate structure we observe today. Over billions of years, gravity patiently amplified the tiny density fluctuations imprinted during inflation. slowly drawing matter together. These initial ripples, mere millionths of a degree in temperature variations in the cosmic microwave background, corresponded to subtle differences in the distribution of matter in the very early universe. Regions that were ever so slightly denser exerted a slightly stronger gravitational pull, gradually attracting more surrounding matter. This was not a sudden, dramatic collapse, but a slow, persistent accumulation, a cosmic ballet choreographed by the subtle forces of attraction across immense distances and vast stretches of time. It was a process of elegant self-organization, where tiny, almost imperceptible differences became the foundational elements for the universe's grand architecture. This gradual accumulation, driven by gravity's patient work, led to the formation of the cosmic web, a vast, intricate network of matter stretching across the universe. Imagine a colossal, three-dimensional spider web, but instead of silk threads, its strands are composed of galaxies, gas, and dark matter. This web is not a static construct, but a dynamic, evolving framework that has grown and refined itself over billions of years. It represents the largest known structure in the cosmos, a sprawling, interconnected tapestry that defines the universe's large-scale organization. The cosmic web illustrates how matter is not randomly scattered throughout space, but is instead organized into a beautiful, coherent pattern, reflecting the underlying gravitational forces that have shaped its distribution since the Big Bang. It is a breathtaking illustration of cosmic self-assembly, a testament to the universe's inherent capacity for intricate design. Delving deeper into this grand architecture, the cosmic web consists of enormous filaments of galaxies and dark matter, interconnected and separated by vast, empty voids. The filaments are the dense, elongated strands of this cosmic network, stretching for hundreds of millions of light-years. Along these luminous threads, galaxies are clustered, drawn together by the collective gravitational pull of the matter within them. Between these filaments lie the voids, immense regions of space that are largely empty, containing very few galaxies and a much lower density of matter. These voids are not entirely devoid of substance, but they are the quiet, expansive spaces that separate the bustling cosmic cities. The interplay between the dense filaments and the sparse voids creates the characteristic sponge-like or foamy appearance of the universe on its grandest scales, a beautiful and balanced distribution of cosmic material. Within this intricate web, galaxy clusters represent the densest nodes, where hundreds to thousands of galaxies reside. These clusters are the largest gravitationally bound structures in the universe, true cosmic metropolises where galaxies are packed closely together, interacting and influencing one another. They form at the intersections of the cosmic filaments, acting as gravitational anchors that draw in surrounding galaxies. These dense regions are not only rich in visible galaxies, but also contain vast amounts of hot, X-ray emitting gas, and crucially, a significant concentration of dark matter. The sheer number of galaxies and the intense gravitational environment within these clusters lead to frequent interactions, mergers, and dynamic evolutionary processes. They are vibrant, active hubs within the cosmic web, showcasing the universe's capacity for grand-scale organization and intricate interactions. An absolutely crucial player in the formation of this grand structure was dark matter, which provided the invisible gravitational scaffolding for galaxies. As we discussed, ordinary matter, the stuff stars and planets are made of, makes up only a small fraction of the universe's total mass. Dark matter, by contrast, is far more abundant, and its gravitational pull was indispensable in the early universe. Because dark matter does not interact with light or other forces, except gravity, it was able to clump together much earlier and more efficiently than ordinary matter, which was initially hindered by the pressure of radiation. These early clumps of dark matter formed gravitational potential wells, invisible structures that acted as attractive centers, patiently drawing in and organizing the ordinary gas and dust around them. It was this unseen framework that allowed the first galaxies to begin coalescing and growing. Indeed, without the unseen pull of dark matter, ordinary matter would not have clumped together effectively enough to form the galaxies we see. The universe would likely be a much smoother, more diffuse place, perhaps a vast, thin haze of hydrogen and helium, with no distinct luminous structures. The initial density fluctuations in ordinary matter were too small, and the universe was expanding too rapidly for gravity alone to overcome these factors and form galaxies within the observed cosmic timescale. Dark matter provided the extra gravitational oomph, the necessary invisible anchor, that allowed the delicate process of galaxy formation to proceed. It acted as the quiet foundational architect, allowing the visible universe to build upon its unseen framework, transforming a featureless expanse into a cosmos rich with luminous structures. Ultimately, the universe's large-scale structure is a direct and elegant consequence of the Big Bang's subtle initial conditions. The tiny quantum fluctuations stretched by inflation, the precise composition of light elements from Big Bang nucleosynthesis, the era of recombination, and the patient, pervasive influence of dark matter all contributed to the intricate cosmic web we observe. Every filament, every void, every galaxy cluster, and every individual galaxy is a testament to this profound and interconnected history. The Big Bang Theory, with its detailed account of the universe's evolution from a hot, dense state, provides a compelling and coherent explanation for the majestic patterns etched across the cosmos. It reveals a universe that is not random but beautifully structured, a harmonious result of fundamental physical laws unfolding over billions of years, a grand design that continues to inspire awe and wonder. As we contemplate this majestic cosmic architecture, we encounter two profound and mysterious components that dominate its composition, yet remain largely unseen. Dark matter constitutes about 27% of the universe's total mass energy content. This invisible substance is far more abundant than the ordinary matter that forms stars and galaxies, acting as a pervasive, unseen scaffolding throughout the cosmos. Its presence is inferred rather than directly observed, but its gravitational influence is undeniable and crucial to the universe's structure. Imagine a vast, ethereal network woven throughout space, quietly holding everything together. This substantial portion of the universe's content speaks to a profound mystery, a hidden dimension of reality that shapes the visible world in fundamental ways, yet remains elusive to our direct perception. Its quiet dominance reveals that much of the cosmos operates beyond the reach of our immediate senses. The reason for its elusiveness is profound. Dark matter does not emit, absorb, or reflect light, rendering it invisible and undetectable by conventional telescopes. Unlike stars that blaze with light, or gas clouds that glow or absorb specific wavelengths, dark matter is utterly transparent to all forms of electromagnetic radiation. It passes through us, through planets, and through stars without leaving a trace of light or energy. This makes it incredibly challenging to study, as our primary tool for observing the universe is light. It is a ghost in the cosmic machine, a silent, pervasive presence that interacts only through the most subtle of forces. This invisibility is not a lack of existence, but a testament to its unique properties, a form of matter that quietly moves through the cosmos without announcing itself through light or any other radiant energy we can directly sense. Its silent nature demands a different approach to understanding its profound influence. Consequently, we infer dark matter's presence and distribution solely through its subtle gravitational influence on visible matter. Scientists observe its effects by studying how galaxies rotate, how light bends around massive galaxy clusters, a phenomenon called gravitational lensing, and how galaxies cluster together on large scales. For instance, galaxies rotate much faster than the visible matter within them suggests they should, implying a significant amount of unseen mass holding them together. This gravitational whisper, though indirect, is incredibly strong and consistent across countless observations. painting a clear picture of dark matter's pervasive influence. It is through these gentle tugs and subtle distortions in the visible cosmic tapestry that we deduce the presence of this invisible architect, patiently sculpting the universe's grand design. Its unseen hand is the silent force that organizes the cosmos. Even more enigmatic than dark matter is dark energy, which accounts for approximately 68% of the universe's total energy budget, making it the dominant component. This mysterious entity is not matter, but a form of energy inherent to space itself, a pervasive pressure that is driving cosmic expansion. Its sheer abundance means that it fundamentally dictates the universe's overall destiny and its large-scale behavior. To imagine something so dominant, yet so unknown, is to truly grasp the profound depths of cosmic mystery that still lie before us. Its quiet, persistent presence shapes the very fabric of space and time, influencing the grand choreography of galaxies across unimaginable distances. This vast, unseen energy is a fundamental characteristic of our universe, a silent force that has been at play for billions of years, guiding its immense growth. This enigmatic force is responsible for the observed accelerating expansion of the universe, gently pushing galaxies apart. For a long time, scientists had expected that gravity, the attractive force of all matter, would gradually slow down the universe's expansion. However, in the late 1990s, observations of distant supernovae revealed a stunning truth. The expansion is actually speeding up. This startling discovery pointed to the existence of dark energy, acting as a repulsive force that counteracts gravity on cosmic scales. Instead of pulling galaxies closer, dark energy gently pushes them further apart, causing the expansion to accelerate over time. This slow, relentless propulsion means that distant galaxies are receding from us at an ever-increasing rate, a cosmic ballet becoming ever more expansive. It is a subtle but profound influence, reshaping the universe's future in ways we are only just beginning to comprehend. The true nature of dark energy remains one of the greatest unsolved mysteries in modern cosmology. Scientists have proposed various theoretical models to explain it, from a constant cosmological constant, intrinsic to space itself, to more dynamic quintessence fields that change over time. However, definitive experimental evidence to distinguish between these possibilities is still elusive. Understanding dark energy is paramount, as it holds the key to the universe's ultimate fate and the fundamental laws governing space and time. It challenges our deepest assumptions about the cosmos and requires new physics beyond our current standard models. This profound enigma is a quiet invitation for future discoveries, a testament to the vastness of the unknown that still lies within the heart of the universe. Its silent presence fuels a vibrant quest for knowledge. In stark contrast to these mysterious components, ordinary baryonic matter, the familiar stuff we can see and touch, makes up only about 5% of the universe. This tiny fraction includes all the stars, planets, gas clouds, dust, and everything else that interacts with light and forms the visible cosmos. It is the matter that makes up you, me, our planet, and all the galaxies twinkling in the night sky. While incredibly important for life and for our ability to observe the universe, it is a remarkably small percentage of the total cosmic inventory. This humble proportion underscores how much of the universe's reality is hidden from our direct senses, governed by forces and substances that remain largely invisible. It is a humbling realization, reminding us that the vast luminous universe we perceive is merely a delicate surface, floating upon a much deeper and more mysterious cosmic ocean of dark matter and dark energy. Within this profound cosmic ocean, the universe is not static. It is a dynamic, ever-changing entity, constantly in motion. The universe's expansion is not constant, but has undergone significant changes throughout its cosmic history. From its initial, incredibly rapid inflationary burst, through periods dominated by radiation and then matter, and now into an era dominated by dark energy, the rate at which space stretches has been a complex and evolving story. Early on, the expansion was incredibly swift. Then gravity's influence began to gently slow it down. However, in more recent cosmic history, a new, subtle force has taken hold, re-accelerating this grand cosmic dance. This varied pace of expansion is a testament to the interplay of different forces and components within the universe, each taking its turn to shape the overall cosmic rhythm. It's a nuanced narrative of growth, not a simple, unwavering progression, but a story with distinct chapters of acceleration and deceleration. For a long period, gravity was expected to gradually slow down the expansion, but the discovery of dark energy altered this understanding. Before the late 1990s, the prevailing scientific intuition suggested that the collective gravitational pull of all the matter in the universe should act as a cosmic brake, slowly decelerating its initial outward momentum. It was a logical expectation, akin to a ball thrown upwards, eventually slowing down due to Earth's gravity. However, the unexpected revelation that the expansion was, in fact, speeding up sent a ripple of quiet astonishment through the scientific community. This profound discovery necessitated a re-evaluation of our most fundamental cosmic models and pointed directly to the existence of an unknown, repulsive force. It was a gentle yet revolutionary shift in our cosmic perspective, compelling us to consider a universe far more complex and surprising than previously imagined. The current rate of this cosmic expansion is precisely quantified by the Hubble constant, which links a galaxy's recession speed to its distance from us. Imagine this constant as a cosmic speedometer, telling us how quickly the fabric of space is stretching. Essentially, the farther away a galaxy is from us, the faster it appears to be moving away, not because it is traveling through space at that speed, but because the space between us and that galaxy is expanding. The Hubble constant provides a direct measure of this stretching, allowing astronomers to calculate the current tempo of the universe's growth. While measuring its exact value has presented delicate challenges, with different methods yielding slightly varied results, it remains a fundamental parameter, anchoring our understanding of how our universe is unfolding in the present cosmic epoch. As space gently expands, light waves from distant galaxies are stretched, causing them to appear shifted towards the red end of the spectrum. Imagine a light wave as a subtle ripple traveling across the surface of an expanding cosmic ocean. As the ocean itself stretches, the distance between the crests of the wave also increases, making the wavelength longer. In the realm of visible light, longer wavelengths correspond to the color red. So, light that was originally emitted as blue or green from a distant galaxy, for example, will appear redder to us by the time it reaches Earth, having been stretched by the intervening expanding space. This elegant phenomenon is a direct consequence of the universe's continuous growth, a subtle but profound signature imprinted on the very light that travels to us. This phenomenon, known as cosmological redshift, is a fundamental piece of evidence for the universe's continuous expansion. It is distinct from the Doppler effect, which describes the shift in light from objects moving through space. Cosmological redshift, by contrast, is caused by the expansion of space itself, stretching the light waves as they journey across the vast cosmic distances. The more distant a galaxy, the more space has expanded during the light's travel time, and thus, the greater the observed redshift. This consistent and pervasive reddening of light from distant objects provides an undeniable, elegant confirmation that the entire cosmos is indeed expanding. A gentle stretching that has been occurring for billions of years since the Big Bang. It is a universal signature of cosmic growth, visible in every direction. Furthermore, redshift allows astronomers to measure distances to faraway galaxies and, by extension, to look back in time to earlier cosmic epochs. By precisely measuring how much a galaxy's light has been redshifted, scientists can calculate how far away it is and, crucially, how long its light has been traveling to reach us. This means that observing a galaxy with a high redshift is akin to looking into a cosmic time machine, witnessing that galaxy as it appeared billions of years ago, when the universe was much younger and smaller. It provides a serene and profound connection to the past, allowing us to reconstruct the universe's evolutionary history, epoch by epoch. Redshift is not just a measure of distance, but a window into the unfolding story of the cosmos, revealing its majestic journey through time. To help visualize how space itself expands, carrying galaxies farther apart, we often use the analogy of an inflating balloon with dots on its surface. Imagine the surface of a balloon covered with tiny dots, each representing a galaxy. As you gently inflate the balloon, the rubber surface stretches, and the dots move farther away from each other. Crucially, the dots themselves are not moving on the surface. Rather, the surface itself is expanding, carrying the dots along with it. From the perspective of any single dot, all other dots appear to be receding, and the farther away another dot is, the faster it seems to move. This analogy beautifully illustrates how galaxies are carried apart by the stretching of space, not by their individual motion through a static space. It is a calm, visual metaphor that helps us grasp the profound, yet gentle nature of the universe's grand expansion. As we journey through the cosmos, we often wonder about its ultimate boundaries. The observable universe is a spherical region of space around us, from which light has had sufficient time to reach Earth. This means it is not a physical boundary in the universe itself, but rather a limit imposed by the finite speed of light and the finite age of the cosmos. Imagine a gentle sphere of visibility centered on us, encompassing all the stars, galaxies, and celestial phenomena, whose light has had enough time to travel across the vast, expanding reaches of space and finally arrive at our telescopes. Everything within this sphere is, in principle, detectable to us, a profound window into the cosmic past and present. It is a tranquil reminder that our perception of the universe is inherently tied to the journey of light through time. Its current diameter is estimated to be about 93 billion light-years, a truly immense scale. To put this into perspective, a light-year is the distance light travels in 1 Earth year, approximately 6 trillion miles, or 10 trillion kilometers. So, 93 billion light-years represents a distance that is almost incomprehensibly vast. This spherical region contains countless galaxies, each with billions of stars, stretching out in every direction from our vantage point. It is a staggering expanse, filled with the echoes of ancient light and the quiet dance of cosmic structures. This measurement is a testament to the patient accumulation of light over billions of years, allowing us to glimpse a truly majestic portion of the universe's grand design. The scale itself inspires a sense of profound wonder and humility as we contemplate the sheer immensity of the cosmos. This vast size is much larger than 13.8 billion light-years, primarily due to the continuous expansion of space during light's journey. Although it might seem counterintuitive that we can see objects that are much farther away than 13.8 billion light-years. The explanation lies in the dynamic nature of space-time. As light travels from a distant galaxy towards us, the space between that galaxy and Earth is continually expanding. This stretching of space means that by the time the light reaches us, the original location of the emitting galaxy is now much farther away than it was when the light first set out. It's like watching a gentle ripple on a stretching rubber sheet. The ripple eventually reaches you, but the point where it originated has moved considerably further away. This cosmic stretching allows us to observe regions that were once much closer, but have since expanded to truly immense distances, revealing a universe far grander than a simple age-distance calculation would suggest. The cosmic horizon defines the farthest boundary of what we can currently observe, a gentle limit to our vision. This horizon is not a physical wall or an edge in space, but rather a boundary in space-time, marking the maximum distance from which light has had time to reach us since the Big Bang. Anything beyond this horizon is, for now, forever beyond our observational reach. It's a serene line of demarcation, beyond which the universe continues its silent unfolding, but its light has not yet completed its epic journey to our telescopes. This boundary is a profound acknowledgement of our observational limitations, a quiet reminder that while our vision is vast, it is not infinite. The cosmic horizon serves as a gentle barrier, inviting contemplation about the unseen realms that lie just beyond our current grasp. Indeed, beyond this horizon, space likely continues endlessly, but light from those distant regions has simply not yet reached us. We have no reason to believe that the universe abruptly ends at the edge of our observable sphere. It is far more plausible that the cosmos stretches on, perhaps infinitely, filled with countless more galaxies, clusters, and voids, all existing and evolving in their own cosmic timelines. These regions are not empty, they are simply uncommunicative, their light still traveling towards us, or perhaps destined never to arrive due to the accelerating expansion of space. The concept of an unobservable universe that extends far beyond our current limits evokes a sense of profound mystery and endless possibility, a quiet testament to the universe's boundless nature. It is a realm of infinite potential, patiently waiting to reveal its secrets. As time progresses, the cosmic horizon slowly expands, gradually unveiling slightly more of the universe to our view. With each passing moment, new light from ever more distant regions has just enough time to complete its journey and reach us. This means our observable sphere is not static. It is a gently growing bubble, continuously expanding, albeit at a slow pace from a human perspective. As billions of years unfold, future astronomers will be able to glimpse galaxies and structures that are currently hidden beyond our horizon. This gradual unveiling is a beautiful testament to the passage of cosmic time, a continuous revelation of the universe's hidden depths. It's a patient process, where the cosmos slowly, gracefully, and unhurriedly reveals more of its majestic secrets, expanding our understanding with each passing eon. Finally, the Big Bang model gracefully describes the evolution of the observable universe, but does not specify what lies beyond its current limits. The theory provides a robust and elegant framework for understanding how the universe originated, expanded, and developed from its initial hot, dense state to the complex structures we see today, all within the bounds of what we can observe. However, it does not claim to describe the entirety of existence, nor does it make definitive statements about regions from which no light has ever reached us. The Big Bang model is a powerful tool for understanding our cosmic neighborhood and its history, but it humbly acknowledges the vast unknown that may lie beyond our current perceptual grasp. This distinction highlights the scientific humility inherent in cosmology, recognizing that while our knowledge is profound, the universe's ultimate mysteries may extend far beyond our current observational horizons, inviting endless contemplation and future exploration. As we reflect on the vastness of the cosmos and its intricate history, we also encounter subtle, almost imperceptible relics from its earliest moments, silent messengers that continue to journey through space. One such relic is the cosmic neutrino background, which is a vast, ancient sea of neutrinos, subtle relics from the universe's first second of existence. Just like the cosmic microwave background, which is the fossil light from about Sol, the cosmic neutrino background is an even older, colder, and far more elusive echo. These neutrinos were created in immense numbers when the universe was incredibly hot and dense, mere moments after its inception. As the cosmos rapidly expanded and cooled, these particles decoupled from the primordial soup, meaning they stopped interacting frequently with other matter and have been streaming through space ever since. They represent a fundamental, pervasive component of the universe, a silent current flowing through all of existence. These ghostly particles rarely interact with ordinary matter, streaming through space almost completely unimpeded. neutrinos are often referred to as ghost particles because their interactions are incredibly weak. They possess a tiny, almost negligible mass and no electric charge, allowing them to pass through vast amounts of matter, including stars, planets, and even entire galaxies, without ever truly touching anything. This ethereal nature makes them incredibly difficult to detect, as they leave virtually no trace of their passage. Imagine a delicate, imperceptible breeze flowing through everything, never quite making contact. This unique property means that the cosmic neutrino background carries pristine information from a time when the universe was far younger and hotter than the epoch of the cosmic microwave background, offering a window into even more primordial conditions. Their unimpeded journey across billions of years makes them invaluable cosmic messengers. To grasp the sheer abundance and pervasive nature of these subtle particles, consider this. Trillions of these relic neutrinos pass through your body every second, silently connecting us to the universe's earliest moments. You feel absolutely nothing, of course, because their interaction probability is so incredibly low. Yet, this constant, imperceptible shower of ancient particles means that we are all continuously immersed in a gentle river of cosmic history, a direct physical link to the first fleeting seconds after the Big Bang. This profound connection is a humbling reminder that even in our quietest moments, we are intimately intertwined with the grand ongoing story of the cosmos, bathed in the echoes of its fiery birth. It is a beautiful, silent testament to the interconnectedness of all things, from the grandest galaxies to the most minute particles. Detecting them is incredibly challenging due to their elusive nature, but would provide unique insights into the universe's infancy. Because neutrinos interact so weakly, capturing even a tiny fraction of them requires enormous, highly sensitive detectors, often buried deep underground or submerged in ice, shielded from other cosmic radiation. While current technology is not yet sensitive enough to directly observe the cosmic neutrino background, scientists are diligently working on advanced experiments that might one day achieve this feat. A successful detection would allow us to probe the universe's conditions at a mere 1 second old, revealing fundamental physics and particle interactions at energies far beyond what can be replicated in terrestrial laboratories. It would offer an unparalleled, pristine view into the universe's very first moments, a profound confirmation of our cosmological models and perhaps even new physics. Beyond these tangible, albeit elusive relics, theoretical cosmology also explores even more exotic possibilities from the universe's earliest fractions of a second. Hypothetical cosmic strings are theoretical one-dimensional defects in space-time, possibly relics from early phase transitions. Imagine these as incredibly thin, immensely dense filaments of energy, stretching across vast cosmic distances. They are not made of matter in the conventional sense, but are thought to be topological defects, much like cracks that might form in a cooling, expanding crystal. These cosmic strings are predicted by certain grand unified theories that aim to describe the fundamental forces of nature. If they exist, they would represent a profound connection between the subatomic realm of particle physics and the grand structure of the cosmos, hinting at an even more intricate initial tapestry. If they exist, cosmic strings could produce subtle gravitational waves or leave delicate imprints on the cosmic microwave background. These immensely dense, thin strands of space-time would exert a gravitational pull, subtly bending the paths of light and matter around them. This gravitational influence could generate unique patterns of gravitational waves, ripples in the fabric of space-time that might one day be detectable by advanced observatories. Furthermore, their presence could leave delicate characteristic distortions in the temperature and polarization patterns of the cosmic microwave background radiation, which scientists are meticulously mapping. Detecting such imprints would provide compelling, indirect evidence for their existence, opening a remarkable window into the extreme physics and phase transitions that occurred in the universe's earliest, most energetic moments, offering a glimpse into a truly exotic aspect of cosmic creation. The detection of primordial gravitational waves, whether from cosmic strings or other early universe phenomena, would offer a direct and profound confirmation of the theory of cosmic inflation. Inflation, as we discussed, was the period of incredibly rapid, exponential expansion in the universe's first fleeting fraction of a second. A key prediction of inflationary models is that this rapid stretching would have generated a background of gravitational waves, ripples in spacetime that pervade the entire cosmos. These primordial gravitational waves would leave a unique, subtle signature on the polarization patterns of the cosmic microwave background, distinct from the temperature fluctuations. Confirming these specific polarization patterns would be a monumental discovery, providing direct observational evidence for inflation and solidifying our understanding of the universe's very birth. It would be a profound testament to the elegant dance between quantum mechanics and the vast cosmos, revealing the most fundamental forces that shaped our reality. Our understanding of these cosmic beginnings is not static. Rather, the Big Bang theory is continuously refined and expanded with new observations and ongoing theoretical developments. Each new telescope, whether orbiting above Earth or nestled in a quiet desert, gathers more subtle light and data, providing fresh perspectives on the universe's history. Advanced particle accelerators explore the fundamental physics of extreme energies, offering insights into the conditions that prevailed in the earliest fractions of a second. Meanwhile, brilliant minds in theoretical physics continue to weave together elegant mathematical frameworks, seeking to unify our understanding of gravity with quantum mechanics, and to explore the implications of phenomena like inflation and dark energy. This continuous process of discovery and intellectual growth ensures that our cosmic narrative remains vibrant and ever deepening, a living story that gracefully adapts to new revelations and profound insights, always pushing the boundaries of human comprehension. Despite these ongoing refinements and the persistent mysteries that still beckon, the Big Bang theory remains the most widely accepted cosmological model, supported by an overwhelming abundance of observational evidence. Its enduring strength lies in its ability to elegantly explain a vast array of observed cosmic phenomena. From the pervasive, uniform glow of the cosmic microwave background radiation, which acts as a gentle echo of the universe's infancy, to the observed expansion of galaxies, patiently moving away from one another, and the precise abundances of light elements forged in its earliest minutes, the evidence consistently points to a universe that began in a hot, dense state and has been expanding and evolving ever since. This harmonious alignment between theoretical prediction and observational reality lends immense credibility to the Big Bang, establishing it as the foundational story of our cosmos, a testament to the power of scientific inquiry to unravel the deepest secrets of existence. Looking far into the cosmic future, the ultimate fate of the universe is still a subject of scientific inquiry, largely dependent on the precise nature of dark energy. The universe's destiny is not yet a closed book. It is a grand, unfolding narrative whose final chapters are still being theoretically explored. The subtle balance between the universe's total matter and energy density, and the mysterious pervasive influence of dark energy, will ultimately dictate whether the cosmos continues to expand indefinitely, eventually collapses, or undergoes some other profound transformation. The precise properties of dark energy, particularly whether its strength remains constant or evolves over cosmic time, hold the key to understanding this grand cosmic culmination. Scientists continue to gather delicate measurements of the universe's expansion rate, patiently seeking to constrain the behavior of dark energy and, in doing so, to chart the majestic arc of our universe's ultimate destiny. Currently, the Big Freeze, or heat death, is considered the most probable fate, where the universe continues to expand, cool, and thin out indefinitely. In this serene scenario, the universe would continue its gentle, unhurried expansion, growing ever larger and more diffuse. Galaxies would drift so far apart that they would eventually become isolated islands in an immense, empty void, their light unable to reach one another. Stars would gradually exhaust their nuclear fuel, cooling into white dwarfs, neutron stars, and black holes. Eventually, even these remnants would slowly fade, and black holes themselves would evaporate over truly immense timescales through a process called Hawking radiation. The universe would approach a state of maximum entropy, a state of perfect, uniform coldness and quiet stillness, where no energy differences remain to drive any processes. It is a vision of cosmic tranquility, a gentle fading into an eternal, peaceful twilight, a quiet and gradual dissolution into boundless, featureless space. While the Big Freeze represents the most likely outcome, other hypothetical fates offer different, yet equally captivating, theoretical possibilities. These include the Big Rip, which might occur if dark energy were to strengthen its repulsive push over time. In this dramatic, albeit less likely scenario, the accelerating expansion would become so powerful that it would eventually overcome all gravitational and even atomic forces, gently tearing apart galaxies, stars, planets, and even individual atoms. Everything would be ripped asunder, dissolving into a final, diffuse, cosmic soup. Conversely, a big crunch is a theoretical outcome if the universe's expansion were to eventually reverse due to a greater density of matter or a weakening of dark energy's influence. In this scenario, gravity would eventually overcome the expansion, causing the universe to slowly, then rapidly, contract back upon itself, collapsing into an incredibly hot, dense state, perhaps reminiscent of its initial moments. These speculative fates highlight the profound interplay of forces that govern the cosmos, each offering a distinct yet equally majestic end to the universe's grand narrative. Stepping beyond the fate of our single cosmos, some grand theoretical frameworks propose that our Big Bang might be just one of many universes, forming a vast cosmic tapestry known as the multiverse. These imaginative theories, often arising from inflationary cosmology or quantum mechanics, suggest that our universe is not unique, but merely one bubble or membrane within an unimaginably larger, possibly infinite collection of other universes. Each of these universes might have its own Big Bang, its own set of physical laws, and its own unique history, unfolding in parallel to our own. The concept of the multiverse is not directly observable with current technology, but it offers elegant solutions to certain cosmological puzzles and expands our perception of what reality might encompass. It is a profound and humbling idea, suggesting that the grand cosmic story we know is but a single thread in an infinitely richer, more intricate tapestry of existence. These grand ideas gently explore what might have existed before our universe or outside its expanding boundaries. If our universe is part of a multiverse, then the question of before the Big Bang transforms from a temporal paradox into a question about the dynamics of the larger multiverse. Perhaps other universes preceded ours, or perhaps they exist concurrently in different dimensions or regions of a vaster cosmic landscape. These theoretical extensions invite us to contemplate the origins of reality itself, moving beyond the confines of our single, observable cosmos. They are intellectual frontiers, pushing the very limits of our imagination and scientific inquiry, continually reminding us that the universe, in its boundless elegance, may hold secrets far grander and more intricate than we can currently comprehend. The Big Bang, therefore, is not just a beginning, but a profound doorway to endless inquiry, a serene starting point for understanding a reality that may be far more expansive than we have ever dared to imagine. As we bring our gentle exploration of the Big Bang to a close, it is fitting to reflect on how this grand cosmic narrative ultimately connects back to each of us on a deeply personal and profound level. The Big Bang provides a direct and fundamental connection between ourselves and the universe's earliest moments. It is not merely a distant scientific theory describing the genesis of celestial objects. It is the opening chapter of our own story, woven into the very fabric of our being. Every particle, every force, every law that emerged from that initial, incredibly dense state has played an integral role in the long, elegant chain of events that eventually led to our existence. This unbroken lineage, stretching across nearly 14 billion years, quietly affirms our place within the grand cosmic tapestry, reminding us that we are not separate from the universe, but an intrinsic, evolving part of it. To truly grasp this connection, we can look within ourselves, for the very atoms that compose our bodies were forged either in the Big Bang itself or within the fiery hearts of ancient stars. Consider the hydrogen atoms that are fundamental to water and organic molecules. These were predominantly created during the universe's first few minutes, during Big Bang nuclear synthesis. They are ancient, primordial particles, direct relics of the cosmos in its infancy. However, the heavier, more complex elements essential for life, such as the carbon in our DNA, the oxygen we breathe, the iron in our blood, and the calcium in our bones, were not formed in the Big Bang. Instead, they were patiently crafted over billions of years within the luminous cores of massive stars, or during their majestic final bursts of radiance. We are, quite literally, made of stardust and primordial gas, a beautiful blend of the universe's diverse chemical history. Indeed, every element heavier than lithium was patiently created by stars living out their luminous lives and then gracefully returning their material to the cosmos. Stars act as cosmic alchemists, fusing lighter elements into heavier ones through nuclear reactions in their hearts. When these massive stars reach the end of their brilliant existence, they often undergo a spectacular transformation, gently dispersing their enriched material back into the vast interstellar medium through grand, final bursts of radiance. This process of stellar birth, life, and death is a continuous, elegant cycle of cosmic recycling. Over eons, this enriched material slowly coalesced into new generations of stars, planets, and moons, each one containing a richer palette of elements. Without these patient stellar laboratories and their graceful cosmic dispersal, the universe would remain chemically simple, and the complex molecules necessary for life would never have formed. Understanding the Big Bang, therefore, offers a profound sense of cosmic history and illuminates the majestic story of our own origins. It provides a comprehensive framework, a serene narrative that explains how the universe evolved from its initial simplicity to its current complex and diverse state. It allows us to trace the journey of matter and energy from the fundamental particles born in the quark epoch, through the formation of light elements in Big Bang nucleosynthesis, the clearing of the cosmic fog during recombination, the ignition of the first stars, and the subsequent formation of galaxies. This grand historical perspective grounds our existence within an epic unfolding drama, revealing that every aspect of our world, and indeed ourselves, is a direct consequence of these vast, ancient processes. It is a story that instills both wonder at the universe's scale and a quiet appreciation for our intricate connection to it. Ultimately, our existence is a direct and beautiful consequence of the universe's long, elegant evolution, rich, complex cosmos we inhabit. The Big Bang set in motion a series of perfectly balanced conditions and fundamental laws that allowed for the gradual emergence of complexity. From the precise initial expansion rate to the delicate matter-antimatter asymmetry and the just right abundances of primordial elements, each step in cosmic history was a prerequisite for the next. This patient, unhurried progression, guided by the subtle forces of nature, has culminated in a universe teeming with luminous galaxies, diverse star systems, and the potential for life. We are living proof of the universe's enduring creativity, a testament to its capacity for generating intricate beauty from profound simplicity. Our presence, a small warm spark within this immense radiant sea, is a harmonious continuation of that initial cosmic impulse, a peaceful unfolding of matter, energy, and time. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the dazzling brilliance of the Big Bang's first moments to the silent mysteries of dark energy. From the tiny quantum fluctuations that seeded galaxies to the pervasive hum of the cosmic microwave background, you have journeyed through epochs of profound transformation. You are part of this cosmic story, not just an observer, but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the legacy of distant explosions. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, and cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.